Hi, I'm Mark Barsamian. In this video, I'll be discussing tangent line problems and applications problems involving exponential functions. This material is from section 3.2 of the book, and more specifically from the tail end of that section, pages 192 to 193, examples 4 and 5. The corresponding homework is this set of 3 problems from section 3.2. Let's start by recalling the derivative rules that we've learned about in previous videos. We have the constant function rule. The derivative of a constant function is 0. We have the power rule. The derivative of a power function is computed that way. We have the sum and constant multiple rule, which gets used a lot. The derivative of that expression is this. And then in the last video, we discussed these 3 new rules involving exponential functions. What I called rule number 1, rule number 2, and rule number 3. I pointed out in that video that rule number 1 is in the book, but rule number 2 is not presented as a rule in the reading. It just shows up in one of the exercises. We used rule number 2 to prove rule number 3. Rule number 3 is in the book. Our first example is a tangent line problem. Find the equation of the line tangent to the graph of this function f of x at x equals 0. Well, remember the strategy for solving tangent line problems. We start by writing down what we are going to do. We are going to build the equation for the tangent line. We'll start by building the point-slope form of the equation for the tangent line, this big equation. And remember the general approach, we start by getting parts. So in this equation, we're going to need an a, we're going to need an f parentheses a, and we're going to need f prime parentheses a. In this equation, that letter a is playing the role of the x-coordinate of the point of tangency. We are given that in the problem statement. The line is tangent at x equals 0, so that's telling us that a is equal to 0. Now to find f parentheses a, we have to use the fact that a is the number 0. And this symbol just means to substitute x equals 0 into the formula for f of x. So the result is f parentheses a is the number 2. And keep in mind that in this equation, the symbol f parentheses a is playing the role of the y-coordinate of the point of tangency. The last part we need to find is this, f prime parentheses a. That does not mean the derivative of a. It means the derivative at a. In other words, we have to find the derivative f prime of x and then substitute in x equals a. So before finding this, we have to first get f prime of x. So our first step is to use the sum and constant multiple rule. Notice that the result of that is that we are setting up the derivatives that we're going to do next. I don't try to do those in the same step. I do them in a new step. The result of those derivatives are going to go here and here. Well, here we have the derivative of e to the x. That's going to be a derivative that we find using our rule number 1. The derivative of e to the x is e to the x. The derivative on the right side, d over dx of x, that's a power function with n equals 1. So we're going to use the power rule with n equals 1. And we clean that up and we're left with 2e to the x minus 3. Now that's our derivative, but remember what we're after is the slope of the tangent line. The derivative is not the slope of the tangent line. The derivative is a function that can be used to get the slope of the tangent line. The slope of the tangent line is this thing, f prime parentheses a. That's the part that we're going to get now. So the first thing we use is the fact that we know that the number a is 0. And then we realize that this expression means to substitute x equals 0 into the formula for f prime of x. The result is that f prime parentheses a is -1. Now that number is the number that's the slope of the tangent line. So we've now got all three of the parts that we need to build this equation. We have our a, we have our f of a, we have our f prime of a. The next thing to do is to substitute those parts into the tangent line equation. We'll do that on the next page. So there's our equation for the tangent line. That's in point-slope form. Now, the standard thing is to present the line equations in slope-intercept form. To do that, we solve for y. So the result is that we have this equation, y equals -x plus 2. Let's go on. Question B is to find the equation of the line tangent to the graph of f at x equals 1. Well, this is going to be a very similar problem. Start by writing down what we're going to do. We're going to build that equation. Remember that that's the point-slope form of the equation for the tangent line. We're going to start by getting the parts. The first part we need is the letter A. Well, that's the x-coordinate of the point of tangency, and we're told that. We're told that the line is tangent at x equals 1. The next part we need to get is this. That's going to be the y-coordinate of the point of tangency. So we get that by substituting the value of A into the formula for f of x. So we have to substitute x equals 1 into the formula for f of x. It's important to remember that we have two functions kicking around. We have f of x and f prime of x. They get used for different things. So we end up with this result that f parentheses a, that is f parentheses 1, is this strange looking expression. That's a number. Remember that e is a number. E is about 2.7, so e is pretty close to 3. So 2e minus 3 is going to be pretty close to 6 minus 3. So in other words, this number, the y-coordinate of the point of tangency, is going to be a number pretty close to 3. Now we need to find that part. That means to substitute x equals a into f prime of x. But we've got f prime of x now. We did that in the previous part. Remember to be careful what function you use. We're supposed to find f prime parentheses 1, so we have to remind ourselves to use the formula for f prime parentheses x, not f of x. So the result is that f prime parentheses a is 2e minus 3. That's weird. That's the same number we got for f of a. But this number down here is the slope of the tangent line. Okay, so we've got our three parts. We've got our a, we've got our f of a, we've got our f prime parentheses a. So the next thing is to substitute these parts into the tangent line equation. Now, when you substitute parts, you have to be careful to substitute the parts in the correct spot. That a equals 1 goes here. That f of a equals 2e minus 3 went here, and that f prime parentheses a equals 2e minus 3 goes here. So what we've got now is the point-slope form of the tangent line equation. So we need to convert to slope-intercept form. First thing that I did is I distributed that 2e minus 3 two places. It multiplies the x and it multiplies the minus 1. And then I add 2e minus 3 to both sides. And when I do that, it cancels. And there's our result. There's the slope-intercept form of the equation for the tangent line. Let's go on. Question C says to illustrate the results of A and B on this given graph of the function f of x. Well, let's go back up and look at our result. Question A was to find the equation for the line tangent to the graph of f at x equals 0. We found that that equation was this. So we have to draw the line that's tangent to the graph of f at x equals 0. Now notice that at x equals 0, the y-coordinate is 2. That makes sense. Remember when we were finding the equation for the tangent line, we found that as our f parentheses a. F parentheses a was the number 2. That's the y-coordinate of the point of tangency. So our tangent line is going to go through that red point. Now the tangent line is going to have this equation. So that's going to be a line with slope -1 and y-intercept at 0, 2. So that's going to be the equation for our tangent line. That means that the line is going to go over 1 and down 1, over 1 and down 1. So the x-intercept of that tangent line is going to be over here at 2, 0. So there's a tangent line with slope -1 that goes through the point 0, 2. That's the result of question A. Now in question B, we had to find the equation for the line tangent to the graph of f at x equals 1. So we have to draw that tangent line. First of all, we find the point on the graph where x equals 1. It's here. Notice that y-coordinate of that point is around 2.5. Oh, that's familiar. Remember a while ago, we found in question B that f parentheses a was this number, 2e minus 3. And I said that would be a number maybe around 2.5. So the coordinates of this point are 1, 2e minus 3. Now, the equation for the tangent line that we got in question B was this. Y equals the quantity 2e minus 3 times x. Notice that that's of the form y equals mx. So that's a line with slope m equals the quantity 2e minus 3, and the y-intercept is going to be at 0, 0. So we have to draw a line that goes through those points. There's that line with slope m equals 2e minus 3. That makes sense, because if we go over 1, we go up 2e minus 3. That's the end of that example. Let's go on to the next example. Example 2. Capital P dollars is deposited into an account that has continuously compounded interest with interest rate R. Question A is, what's the value at time t years? Well, this is just asking us to recall the formula for the balance of an account with continuously compounded interest. That's it. That's the formula. Now, question B says, what is the instantaneous rate of change of the balance at time t years? Well, this question is asking you to make the connection that instantaneous rate of change of the balance just means capital A prime. Now, we should be a little bit clear here. This equation is an equation involving letters A, P, R, T. But in question B, we should think of that equation as a function. A as a function of the variable t. So we should think of capital P and little r as constants, think of little t as the variable, and think of capital A as a function of t. So let's start by rewriting that equation in function form. So when we find capital A prime, we are taking the derivative of that function, and the variable is t, not x. So the derivative is going to be d dt, not d dx. So the result is that this derivative, capital A prime of t, is equal to this, r times capital P times e to the rt. Hey, that's kind of interesting though, because notice that in that final formula, we have the expression that's the expression for capital A. So let's clean this up some more. Let's do one more step. So the final result is that capital A prime parentheses t is this expression, but that could be thought of as little r times capital A of t. That's the end of example 2. Let's go on. Example 3. An investment of $1,000 earns interest at a nominal rate of 7% compounded continuously. What's the value at 10 years? Well, we're supposed to make the connection that if you have an investment earning interest that's continuously compounded, then it behaves according to that usual formula. So there's the formula for the balance of an account that has continuously compounded interest. Now let's think about what we know and don't know in this equation. So what we are being asked to find is the value of A. So we just substitute our known quantities into that equation and we find the value of A. There's our exact value. We are asked for an exact answer in symbols. We're being asked to find a decimal approximation, so we'll type in this expression into a calculator. So the result is the balance is roughly 2013.75 cents. Let's go on. Question B says, how fast is the value growing at time 10 years? Well, the key here is that we have to make the connection that this means that we're being asked about the derivative. So we use the formula for A prime of t. So we get the exact answer, 70 times e to the 0.7. Now we need a decimal approximation. We type this into a calculator or into Wolfram Alpha. So there's our result, that A prime parentheses 10 is roughly 140.97. But we have to do a bit more. We're supposed to include the correct units. This is a rate of change. How fast is the value growing? So the units of this are going to be whatever the units are for the value divided by whatever the units are for the time. So that's our rate of change, roughly $140.97 per year. Let's go on to the next part. Question C says, how fast is the value growing when the value is $8,000? Well, so we're being asked to find the value of A prime, but it's kind of strange because we're not given the value of the time. So what do we do? Well, you might think that we need to find the value of time and use that to find A prime parentheses t. So let me outline that. Turns out that's not what we should do, but I'm going to outline that as what we might think we would have to do. So one might think that we have to use the fact that A is 8,000 to find the value of t. Turns out that's hard. And then one would use that value of t to find a prime of t. Well, that's also hard. So one might think we would have to do this difficult process. Well, the trick here is to not do that difficult process. The trick here is to remember what we know about a prime parentheses t. Let's go back up and look at our formula for a prime parentheses t. When we found a prime parentheses t, we found that it was given by this formula, and then we recognized that in that formula was this expression, which is the expression for a of t. So in other words, a prime of t is just whatever the value of a of t is multiplied by this extra little r. So it turns out we don't ever have to find the value of time. We can just use the given value of the balance, $8,000, and we can use the interest rate, R. So the result is that a prime parentheses t, whatever the time is, we don't know the time, is $560 per year. And again, note that units. The units are whatever the units are for the value, which is dollars, divided by whatever the units are for the time, which is years. So there's our answer. Go down to question D. Question D says to illustrate the results of questions A, B, C on the given graph of that equation. That's the equation for the account balance for an account with continuously compounded interest where the value of P is 1,000 and the value of little r is 0.07. Okay, well, let's go back up and review our results. In question A, we found the value at 10 years, and we found that it was roughly $2,013. Well, that's going to be illustrated by putting a point on this graph. The y-coordinate of that point is the balance at time 10 years. The balance is roughly $2,013.75. So that's pretty close to 2,000, just a little bit above that grid line. Let's look at our question B results. Question B was, how fast is the value growing at time 10 years? And we found that the result was roughly $140.97 per year. But that's denoted by that symbol, a prime parentheses 10. That's the slope of a tangent line. So we should illustrate this result by drawing a tangent line and indicating its slope. Now what about our answer to question C? Question C was, how fast is the value growing when the value is 8,000? And we found this answer, $560 per year. Now that's denoted by this symbol, capital A prime parentheses t, but we don't know the value of t. But we do know that the value is 8,000. So all we need to do is find the place on the graph where the value is 8,000 and draw the line tangent to the graph at that point. And that line is going to have a slope of 560. Well, there's our 8,000 as the value, and so there's the point on the graph with a value of 8,000. We don't know the time. That's down here, close to 30. We never did need to find that time, but we just need to draw the tangent line at that point and put its slope. And there we go. That's the illustration of results of A, B, and C. All right, let's go on to one more example. Example 4. The estimated salvage value of a new car is described by this function. In this function, the variable t is the time in years since the car was purchased, and the function s parentheses t gives the salvage value at time t, in other words, the value. So question A is, what was the purchase price of the car? Well, the car was purchased when time was 0. So we're just being asked for S parentheses 0. So the purchase price is $65,000. Oh, we could just have spotted that. It's just sitting there in the formula. Question B, what's the value of the car at time t equals 6 years? Well, we have a formula for the value of the car, so we're being asked to find S parentheses 6. So there's our exact answer. But we're also supposed to provide a decimal approximation. So here's my usual style of solving these problems. I write down the solution in symbols first. That's the exact answer. In the very last step, I type that stuff into a calculator. The result is 24515, roughly. And that's in dollars. The correct units are whatever the units are for the function S parentheses t. I should have said here that the salvage value is given in dollars. Okay, let's go on. Question C says, what is the rate of change of the value of the car at time t equals 6 years? Well, the connection we have to make is that this means to find capital S prime parentheses 6. So the strategy should be find S prime parentheses t and then substitute in t equals 6. So there's our strategy. Let's do it. So there's our result. Notice the first step we used the constant multiple rule. In the last step we used rule number 3. Remember what rule number 3 says. Rule number 3 says the derivative of b to the x is b to the x ln of b. So in our current problem, the value of b was 0.85. Now we can clean this up a little bit. So here I just simply put all the constants in front. Now we have to substitute in t equals 6. There's our answer. That's our exact answer. We type that into a calculator. And the result is roughly minus 3984. Now we're supposed to use correct units. So the units are going to be whatever the units are of the value divided by whatever the units are for the time. Now that might seem strange that S prime parentheses 6 is negative. But remember, this is a function that describes the value of a car. And the value is decreasing, so it makes sense that S prime is going to be negative. Question D is to illustrate the quantities from A, B, C on this given graph of the function S parentheses t. Now, before we do any of that, notice the shape of this graph and the form of the function. The form of the function is an exponential function with base 0.85. Notice that the base 0.85 is between 0 and 1. So we know from a previous video in our discussion of exponential functions that that's going to be a decaying exponential function. Sure enough, we see that this graph has the shape of a decaying exponential function. All right, let's go back up and look at our results from questions A, B, and C. In question A, we found that S parentheses 0 is 65,000. Well, that's going to show up as a y value on the graph at time t equals 0. So here's the place on the graph where time is 0. So the y value is $65,000. Now let's look at our results from question B. Question B, we found this. S prime parentheses 6 is roughly $24,515. Well, that is a y value on the graph where time t is 6. Time t equals 6 occurs here. So this is the point whose y-coordinate is $24,515. Now question C. Question C, we found this. S prime parentheses 6 equals roughly minus 3984. Well, S prime parentheses 6 is the slope of a tangent line, the line tangent to the graph at time t equals 6. So we have to draw that tangent line and label it with this number as its slope. So you see that the value of the car is going down, and that tangent line has a negative slope. All right, that's the end of the example. That's the end of the video. Thank you.